pleased to have for our special Simon's Colloquium today Vladimir Zakharov from University of Arizona, who will talk about the search for integrable systems by means of perturbation theory.
Okay. Actually, it's a kind of long lecture. First, I discussed results obtained approximately 20 years ago. Then I will discuss results which obtained right now, and then I will formulate an answer question, enigmatic, and show some results of numerical experiments, which are really very exciting, in my opinion. The question is about integrable systems. You know that during the last 30 years, the theory of integrable system was flourishing, and many integrable systems were found, but still the question, if you have some nonlinear equation, is it integrable or not, it's not answered. And I try to find some approaches to the solution of this problem. Of course, there is no, I do not believe that it's possible to find a universal algorithm for such, to answer this question. However, some important necessary conditions can be really displayed, and they are actually a lot of information can be extracted from the analysis of perturbation series of this system. So this is actually approach is traditional. It's coming back to at least to Poincaré, who studied the system close to integrable and try to find a condition which are should be satisfied to preserve integrability, and he found that this condition are very rigorous and strict, and in a typical situation, obstacles appears like small denominators, and so in a sense my talk is a continuation of Poincaré ideas but what's the difference? That Poincaré studied the system with finite numbers of degrees of freedom. I will speak about a wave system which have infinite number of degrees of freedom and which also have a translation group. So it's a homogeneous system. And this is very important point, homogeneity, which make many things completely different from the case of finite dimensional case, which is certainly has nothing in common with homogeneity. And homogeneity, in a sense, simplify the situation and makes possible to build a bridge with quantum field theory and with a theory of scattering matrix. In a sense, what we do, we study a scattering matrix in the system, but in the classical system, so there are only diagrams of three of type without loops. They included in, and this so the condition is cancellation of scattering imposes functional equations to basic functions describing the system. Sometimes it's possible to solve this functional equation in this completely rigorous way and to prove the theorem that such a system as integrable, such are not integrable. However, still some very important physical problems are not answered, and because just because of lack of shortage of time, because with all this technique is very cumbersome in the sense of calculation. You even to prove some theorem, which in our last work with Adesky, we've used the Maple possibility, whole power of Maple system, and working for a couple of hours before it made an answer. But direct numerical experiments, just solving dynamical systems directly, which again refer to first experiments of the Pascal, which are foundation of theory of integrable systems. They are still in process, and the results sometimes are extremely interesting, and I will show some movie in the end of the talk. But let me first formulate some basic ideas, because this audience is ideally mixed. You forgive me if I will start with extremely simple things, and then I will go further and further. And first I write just a Schrödinger equation, linear Schrödinger equation. In space of dimension d, it's a Hamiltonian system. It's a Hamiltonian is integrable gradient psi squared in the R. And if I introduce A and K, it's a Fourier transform of this function. The Hamiltonian now is just the integral k squared ak modulus squared dk. And equation now turns to following form. ak dot is minus I delta h by delta ak star, which is minus omega and k and k. Omega and k is a squared. Sorry, it's very trivial, of course. I said nothing in the rest. My next example is almost such the same level of triviality, a little bit less. If I start with wave equation, I also can turn into the system, to such system. Just first I present it like a system of, well, I'm going to make Fourier transform. Then equation UB, UC is VK, and VT is minus k squared U. And then I introduce the normal variables like this. K minus plus A minus K bar U VK is minus K by 2 AK minus A minus AK. So everybody who studied quantum will surely know that what I did is the first step before second quantization. This is A, can be now stated as operator. I can say, okay, suppose U is the operator and my AK, and it's an annihilation operator, and my AK bar is the creation operator, right? And now I work in classical systems, so I see numbers, but again, my equation is exactly like this. My omega now is modulus k, right? This is a linear system. Next example, probably, if I go to the nonlinear system, I a little bit modify this equation.
See, what aspect of this first one is related to what you call integrability?
Because it's a linear system, all linear systems are integrable, right?
It doesn't matter. My question is, what aspect of the marks on the blackboard are related to integrability?
You will see later, right?
Huh?
Later on, just in a few minutes I explain. Just in a few minutes. So of course, this system which I discussed, they are written in such form. They are integrable just because they are linear, right? That's integrable system, and they have infinite number of motion constant. For instance, I can find any function, real function f of k, if f is star, and if I calculate f of k, ak squared dk, di by dt is 0, right? For any choice of f. In linear systems, it's not a big deal. Now what I will do, of course, I will a little bit spoil these equations. And for instance, instead of this equation, I will write following equation. UTC equal Laplacian u minus epsilon Laplacian square u plus Laplacian u square. Well, that's nonlinear equation, right? It's nonlinear equation. But this again can be transferred to this form. And it takes some skill to do this. It's not that simple. First, you should, all right, again, you should turn it to the system of equations. And the system is following system. ut is minus Laplace of phi, and phi t plus u plus u squared minus epsilon Laplace u is 0. This is the same system, of course. Now one can see that it's like a little bit mutilated gas dynamic equation, right? This resembles coming back to continuity equation, and this is coming back to Bernoulli equation, where phi is hydrodynamic potential and u is density variation, and this is a Hamiltonian system. So the Hamiltonian system, ut is delta h by delta phi, and phi t is minus delta h by delta u. H is some Hamiltonian, which is actually following Hamiltonian, Laplace phi square plus integral on u, 1/2 u squared plus u 1/3 u cubed plus epsilon by 2 plus u squared dr. And again, I can introduce normal variables like this. U and k is 1 of root square, a and k, b and k, 1/4 ak plus a minus k, and yk is pi by 2, b dk by ak in 1/4 minus here ak minus a minus k, right? So a on k is k squared, and b on k is 1 minus f plus epsilon k squared. So if I would like to construct the quantum theory of this system, I will start with this, right? And I will say, okay, my operator are now, should be replaced to operator of creation and annihilation, and I plug to my equation. But now it's again, it has this form. However, now it is also has nonlinear part, right? Because it's nonlinear equation. A nonlinear part is relatively simple. Is 1/3 u k k1 k2 ak ak1 ak. Oh, sorry. K plus complex conjugated delta k plus k1 plus k2 dk dk1 dk2 and plus v. Now these two terms are actually the same, and you are just coming from here. k1 k2 is 1 root square into pi by v by 2 root square 2, and this is just product a k y k2 bk1 bk2 1/4, and the next term is more interesting. So to describe the same actually Foucault coefficient, but u ak star ak1 ak2 plus complex conjugated delta k minus k1 minus k2 dk dk1 dk. So what is conclusion? What is the result of this experience? That many systems, all reasonable systems, can be, by proper choice of variable, they can be in homogeneous system, they can be presented as such form. And where the Hamiltonian is, well, I speak only about system with one type of waves, and my Hamiltonian is, so it's enough to show you that I could start with this, but without these examples it would be not very understandable why I do this. So I study the system of such type.
Can I ask a question about this example?
Yeah, sure.
The conservation laws? Conservation laws?
Yeah, I just will speak about conservation. It's the next question which exactly I have. And your H is H naught plus H interaction for everybody from physics. It's a completely trivial fact. The H naught is just integral omega on k, ak. Just usually on quantum mechanics they write like that, right? It's a normal ordering, but for our cases, no matter how to order them. And what is H interaction? So to make it a compact form, I can just use the following additional symbol S. So it is just AK k1, s is plus minus 1. S minus 1 on k is a star on k, right? And now my Hamiltonian H is H3, it's a series. And H3 is some integral V 0, 1, 2, S1, S1, S2, A, S, K0, K just A, S1, K1, A, S2, K2, delta, SK plus SK1 plus SK2, dk, dk1, dk2. And then higher order terms, they contains higher degrees, right? You can construct, of course, H5. Now the question about motion constant. This is a central question. Can I construct a motion constant like this? Can I start? Can I do as I guess? Can I behave such as I behaved in the linear system? So, can I choose any function f of k and say that okay, my motion constant is a0 plus a1 plus a2 plus. And the first term will be exactly p of k, ak star, a of k, ak. And then the next terms are also polynomials, monomials, or on this. If I can do this, this system is integrable, right? And there are many examples where I can do this. For instance, for equation, for Bussing-esque equation in one dimension, I can do this. I can start from any arbitrary function, but it is enough to start from, suppose, to consider that f on k is k in power n, right? And then you add further combination, and then you will continue your integrals. So if in Schrödinger equation, I have several options. For instance, I can consider here just psi squared psi. In this case, I have infinite number of motion constant. But that's not all. I also can study following equation: psi x plus minus I psi squared psi x. Again, it's possible. It's the integrable system has the infinite number of motion constant. Moreover, I can do like this: d by dx psi squared psi. It's a divide equation, of course. Again, it has a different Hamiltonian structure, so you need to make some work to find the normal variables in this case. I started with this because this looks like a very trivial step, but important. Anyway, there are the so-called differential non-reducing equations, and they are integrable. Another system is
So how
Cartesian difference.
how do you know that you have enough of these integrals to declare that it is integrable?
Yes, it's proven that's enough. For at least for this case, it's proven that you can introduce accidental variables. Look, book 10 and 5.
But for those who
Yeah, it's enough. It's enough.
This is a colloquium, it's not a seminar, right? So
Yeah.
you're supposed to assume that we know nothing. So what's the definition?
Yes. So, what was the question?
Assume there is a definition.
Yes. Is there a definition, and if so, give it?
The definition. Yeah, so far I formulate a very narrow question. Existence of, so of course, some integrals are known, right? For instance, you can start with omega on k, and this is your Hamiltonian.
So
You also can put this k, and that is your momentum.
So
And the
this-
question is, could you construct at least one extra motion constant? This is not enough for integrability, but it is still very serious question, because when you try to do this, you see obstacles. And let us try to do this for a system with 3 wave interaction.
So can I ask one more question? So is it correct to say that the motion for the system would be some kind of quasi-periodic motion?
In all these systems, yes, of course.
So
It's
this would be
quite a
the
periodic motion, but yes and no, because it's not that, in the simplest cases, yes, but in a general case, probably situation is more difficult.
But would
But
it be...
anyway, so far I speak only, I don't speak about motion, about the character of motion. I'm only speaking about existence of extra motion constant, nothing more. And I tell you that even this question is extremely difficult. And let me consider that I have in my Hamiltonian, I have the following term. V 0, 1, 2, A K star, A K 1, A K 2. Plus AK, AK1, star AK2, star, delta function, K minus K1 minus K2, dk, dk1, dk2. This is my first term in my Hamiltonian. If I construct, so if I like to find the extra motion constant, it starts from function f from k, ak, ak, dk. You find that the next term will be like this. It will be f 0, 1, 2, ak star, ak1, ak2, plus complex conjugate, delta k minus k1 minus k2, dk, dk1, dk2, where f 0, 1, 2 is phi k minus phi k1 minus phi k2 divided by omega k minus omega k1 minus omega k2 multiplied to this v 0, 1, 2.
So excuse me, what did you do? You started with some term and then you said there is a next term that we
It
know.
should be like this.
How do we know this?
Well, just plug into equation and
So we're doing perturbations here.
yes, of course. You just plug your conservation law. You differentiate your conservation law, and you apply this equation, right? And use this equation. And you step by step. I think I am in a mathematician seminar. My theory is absolutely formal. I completely do not care about conversions of this series. They're formal series, just formal series. Formal series is some set of expression written in paper, right? And there's an algorithm how to construct the next one.
Formal is fine for us. What we like is the statement that the problem is the following, and then there are some statements like, if X is true, then Y follows.
Yeah, I tell you that if your constant do exist, that the next term should be like that. That's a very simple statement, right? You have any question? Why? You just differentiate. You differentiate this, and you plug in your equation. You start with your equation dAk by dt minus dk minus I some term, nonlinear term, which is v 0, 1, 2. So some equation coming from these, right? I take this equation, I differentiate this, I use this equation, and I immediately get this result. And now it's a question that I'm working on also on the manifold. And now I have a choice. It should be finite. There are two possibilities. Number one, if there are actually three possibilities. Probably there is no you need to work. There is another condition of order. The first question, could I find a solution of this equation? It depends on the shape of my function. I usually have a trivial solution. For instance, k1 equals 0, right? If omega on 0 is 0, so one trivial solution. But in most physical cases, in this trivial solution, v is also 0. So I don't care about this trivial case. So there are two possibilities. If this equation has solution or they have no solution. If they have solution, if they have no solution, I have no problem at all because my denominator cannot be small, and then I can make a canonical transformation and exclude cubic terms from the Hamiltonian without any problems, and go to the next level. This is why I get nonlinear shrinking equation and so on. But if this solution really do exist, I have other parts. So if I have small denominator, I have two other opportunities. First, that my coefficient is 0 on this manifold, or my numerator is 0, such that I have a cancellation. If the numerator is 0, it means that there is some another function which satisfies the same condition. In this case, I will say that my dispersion relation, omega on k, is degenerative. And it is possible to describe all degenerate dispersion relation in the space of dimension 2 if K is PQ. This is a subject of a chapter of differential geometry called web theory. Web theory,
Web explains by Chern.
In the sense of
web
trim.
theory. And I only show you the simplest example of the generated dispersion relation. Suppose that I have the following parameterization. My K is PQ, right? Is P is I from psi minus I from beta. Q is P times psi minus P times beta. Omega is gamma psi minus gamma. Alpha, beta, and gamma, 3 functions of one variable. Then I can say that my dispersion relation phi can be presented like this: f of psi minus f of beta. F any arbitrary function. This is the generated dispersion relation. And interesting to show, to look what kind of equation I will give. In the simplest case, if I consider that P is psi minus, that alpha is just psi, beta is psi squared, and gamma is 4 psi cubed, I get that omega is P cubed plus 3 q squared by P. So it's a dispersion relation for very known Kazantsov-Pitvashvili equation.
So could you explain somehow generically how one?
Yes, it's possible to degenerate, and
I'm sorry, I was asking.
if I can construct if PQ and omega are polynomial, actually so polynomial that this corresponding integrable system can be constructed in explicit form by the using of D-bar method, which developed in our.
In general, how would I want to think of if I want to think of geometrically, what is a dispersion relation? Or if I want to think
It's
physically?
of course a transfer surface.
Yeah, so in what generality do such things exist? How many are known?
Yeah, I think that if you have infinite degeneration, so if you have infinite number of function f, function phi, compatible with this only the full description. But there are some exceptional cases when you have only finite number of functions. And one of the most interesting cases is dispersion relation following function. Omega is P 1 plus P squared Q squared. This is a dispersion relation of Rossby wave in atmosphere. And in this case, there are only 2 extra motion constants, which were found by former students such a bulk. I give you formula of them. They're very nice. It's again the theorem, only 2, and then I should find somewhere. Yes, they are following. They're given by the following formula. It is just a real and imaginary part of the following function. Logarithm q1 root square 3p plus ip square q minus root square of p minus ip square. P square is p square plus q square. So in this case, you can overcome the first. So if you can somehow overcome the first obstacle, right? You can do this by 3 different ways. Suppose you have no denominator at all, and you have v equals 0. If you have a degenerative dispersion relation, then you go to the next step. You will face with the next obstacle, right? When you try to continue your integral, so far we move up very slowly. It means that we have now h, and we have now we have to work with the next term, and then you find that you have to introduce the following theorem now. I formulate. I find a sufficient condition for existence of motion constant in the form of formal series. Again, I don't say about conversion.
What parameter are you determining?
The parameter is not linear, suppose I suppose that A is, so I can put here a small parameter. So what I will do now, I will multiply my H interaction to E in minus epsilon modulus T. H interaction, right? So it's a good adiabatic including of interaction. And now I can write my equation like this. A on K, I can solve my equation like this. A is a K minus plus some integral minus or plus. And then with something integrating by time, right? It's very simple. So this is, and a K tends to a minus K, and T tends to minus infinity. So far as I have finite epsilon, I absolutely have no problems with divergent integrals. No. And then I do solve this equation formally, and I find A plus. And I do find that A plus is a minus plus some series. And as I call this operator epsilon A minus, some nonlinear operator. And then I send epsilon to 0. And I call this formal scattering matrix. And my statement is following. If my formal scattering matrix is trivial, then I can construct extra motion starting from any function phi.
Trivial, you mean diagonal?
No, just I think it should be a little bit made in details. Actually, this S is a function of well, it's like a diagram, right? With and coming and going up, right? Suppose it's S and M. It should be trivial if it's not just a completely elastic scattering. If the scattering is elastic, it means that M equal to M. And its coefficient depending on K1, Kn, Kn plus 1, Kn plus n. And if all these K kn plus 1, just outgoing weight numbers is the same as coming in, right? It could be not zero, but it is not obstacle for integrability.
It is diagonal.
This diagonal part, yes. If it's so, if it's of diagonal part is non-zero, is zero, I can construct a constant. So, but it's very difficult, of course, statement. And however, how I formulate a theory, following theory. I will look for a question like this. Ut is omega u plus ux. Omega is some operator like this of type of converse. A first non-trivial element of my scattering matrix now is a 5-wave interaction. 5-wave interaction is when 3 vectors are coming and 2 are outcoming. So it's a coefficient S dependent on, suppose this is K4, K5, it's a K1, K2, K3. It's a K4, K5, K1, K2, K3. By the way, I should say that this result was obtained in our work with Schulman about 20 years ago, but what I'm talking now is completely new result in collaboration with Sasha Desty. And now I like this zero in virtue of the following equation: K4 plus K5 equal K1 plus K2 plus K3 omega K4 plus omega K5 equal omega K1 plus omega K2 plus omega K3. I say that there's only 3 functions satisfying to this condition. First is omega in K is Kq. This is a characteristic de Vries equation. In this case, it is just one of 9. K1, K2, K3, K4, K5, K4 plus K5 minus K1 minus K2 minus K3. It's very easy. You can do this. In spite of this expression for S, including both diagrams of such type, of 5 to 2 diagrams of this type, with different possible distribution of errors. It includes 15 terms. That could be done easily. Second test, omega on K is K squared. It's a called Benjamin equation, appearing as a theory of internal waves. And it takes 2 pages of calculation, but it could be done by hands. But the number 3 is a K squared E in K plus 1 E in K minus 1. But this to check now, it takes a 1 hour work of Maple, because when you plug this in S, you find that exponents are algebraically dependent on powers. So in fact, you can consider that A and K is the new variable. And so it's a polynomial of how many? Of 10 variables, right? And this belongs to the ideal which is constituted by these equations. So it's not easy to check. Yeah, it's a classical problem of algebraic geometry. If you have a polynomial, it belongs to some ideal. But anyway, it was done. And moreover, if you assume now the theorem, if you assume that your omega is an analytic function, it's in vicinity. So start from linear part can be excluded. A1, K2 plus A2, K2 plus A3, K3 plus other. Then A2, A3 is 0. And so this describes all possible terms. All possibility are described by. There is no other equations. Only from physical viewpoint, it means that you can now put here P and Q. It consider that it's another coordinates, right? Because they really, of course, algebraically independent. So it means that instead of one-dimensional equation, you got two-dimensional equation, which was not known before. Let's say du by dt, which is d2 by dx squared, cot hyperbolic d by dy of u plus ux. So the article is already written and sent to for publication. No more equations. So actually,
This is some difference equation, right? So
it's not different. It's an integral equation, right? Because when you make go to Fourier transform, yes, you go to integral. Now I have only. Now I said about mystery, right? And what's about mystery? The mystery is if we study wave from deep water, aerodynamic, a free surface of potential flow. So it's greater than 5, right? Free surface hydrodynamic in the gravity. And again, after some hard work, you can, not very hard work, you can present it as a Hamiltonian system. Your Hamiltonian will be H0 plus H1 plus infinite series. There is an algorithm how to calculate higher terms. The dispersion relation now omega k is root square on gk. In this case, there is no first obstacle because it's not dispersion relation, which does not allow three-wave processes, so we can go further. And then the miracle, when you want to calculate, you start to calculate scattering matrix, the matrix C2 element is here. We don't know why. As a result of long calculation, I say that it's not a diagonal element. Suppose it's omega on k plus omega on k1 equal omega on k2 plus omega on k3. K plus k1 is k2 plus k3. So suppose my k is 9, k1 is -1, k2 equal k3 is 2, right? So you get 3 plus 1 is 2 plus 2. It's non-diagonal element. But for a mysterious reason it is 0. Is it an integrable system or not? So we calculated 5-wave interaction. 5-wave interaction, in this case 5-wave interaction includes, they separate in 9 different cases, depending on mutual position of vectors. In 2 cases, coefficient is 0. In 7, it is not.
So it's
Not integrable at that level. However, we have some mysterious cancellations. And what's going on if we go to the 6th order? No, it's probably above of human capacity, because the number of diagrams, even in 5-wave case, are about 70 diagrams. And for 6-wave, it will be about 1,000 diagrams. Yeah, it's not possible to calculate or variation of errors. However, we can solve directly this equation, exact Euler equation in computer, and look what happens. One of the first questions is following: do a solitonic solution exist which for a long time in non-integrable system, this solitonic solution must not exist. It must radiate in backward direction. And the second question is, how solitonic solution if they exist interact? And now I show you more this. Yeah, resources better in place. Yeah. So we start with some initial. Now we solve exact equations, exact Euler equation for free. We're using conformal method to work. I don't go to details. It's work with Yachenko. And now you see formation of solid, who leaves thousands of its own periods. Yeah, you can continue. You look at time. Time is in his period. You can go for thousands. It's still existing. Very persistent. It may change a little bit its form, but it still works. Okay, now the interaction of 2 solitons. Okay, we can show them.
So it's exactly like KDB, right? So this is
Yeah, that's because it's a complex function. When we just play on the real part when they intersect. This is fascinating. The last movie is that's what's going with the spectrum. You see, when the soliton overlap, the spectrum is going forward. You asked me about quasi-periodic behavior.
Yeah.
This is exactly quasi-periodic behavior. But so far, what we know is just some of elements of matrix scattering are mysteriously consonant, not all of them. So still enigmatic situation.
So, sorry, the statement is that it's not integrable.
It is, no, I didn't say so. I say that it doesn't satisfy the sufficient condition of integrability. Sufficient condition of integrability, so we don't know. We certainly, we cannot prove integrability. But some necessary conditions, but only part of them are satisfied. And, well, this is still, I don't know, we will use some new ideas how to, we need some new ideas to move further in this direction, because just continuation of calculation of higher order terms is so difficult. This really takes even in fast wave interaction, what map was on the limit of its ability. Probably we will study more solid-onic solution, and so we need some insight, and we have some ideas, but probably they are, I will keep them for another talk, because they are completely different circle of ideas. Actually, we can construct some concept of motion, but how they are connected with this concept of motion is so far completely unclear. It's, yeah, so far I don't like to touch. So far I say that the system is under strong suspicion of deep surface. But, okay.
Is any known integrable system?
Let's not speak first.
The question
Is any known integrable system for which S is not equal to 0? For which the statement is not?
Yeah. Yes. Yes, they are. And it's a good question. If you have the following equation. This is Kepler's differentiation, right? Well, if you add here following term, as I call lambda, 3 lambda, d minus 1 d u by d square equal to 0, d minus 1. This is so-called KP equation, and there are two different KP equations where lambda is 1, lambda is 1, it is KP1. Lambda is minus 1, is KP2. In KP2, it's integrable system. Manakov proved that A plus equal A minus. So 0. The scattering matrix is 0 in any orders, and you can construct when you look at cancellation of a partial elements. Each cancellation looks like a miracle in algebraic geometry, that the huge polynomial becomes 0, it belongs to an ideal constructed by lower polynomials, right? But still, this is correct. But if lambda is 1, the scattering is not, this dispersion relation is now degenerative. And when I told you that alpha is psi, beta is psi squared, and gamma is 4 psi cubed. And you can construct infinite number of motion constant, but not starting from arbitrary function phi. Only starting from the dispersion relation which is compatible with this, right? So your functional phi, pq, must be following f q by p minus 1 minus f q by p plus phi, right? F is arbitrary function. So the number of your degree of freedom is much less. And in this case, your scattering is not trivial, and S plus is not equal to S minus. They are different. However, from physical viewpoint, it means that the scattering going only through the real processes. All virtual processes are zero. So your scattering matrix is factorized at each level. It's a factorized of consequence of three-wave interactions. So it means that you have, in the general case, you have delta function k plus k1. Suppose this is k1, k2 plus 3. Like this. In a general case, you have condition k plus k1. Your delta function k minus k2 minus k3 multiplied the delta function omega k plus omega k1 minus omega k2 minus omega k3. It also, now in the scattering matrix, you have following k plus k1 minus k2 minus k3 multiplied to two delta functions, k plus k1 minus omega k plus k2 delta omega k2 plus k3 minus omega k2 minus omega k3. So it means that the scattering matrix is non-trivial, non-zero on the submanifold of codimension 1 with respect to the all other is when you make a final limit epsilon tends to 0, you should be very accurate with the poles, right, which go to, and some elements give you delta function, some elements give you principal value. So all elements which give you principal values are constant. But what remains only a result of taking delta function in any vertex. This is very non-trivial fact, but it's and this is again a general fact. I can construct any number of systems which satisfy to the same property by the using of debug method. Well, so we see that, but indeed, could we construct the next extra constant of motion for water waves? In direct matter, if you just try to do this directly. It's extremely hard work, but probably we will try to do this, but I don't know what will. We are certainly not sure that we will get non-trivial result. That might be zero, I don't know. So the situation in the science is a difficult thing. Sometimes you cannot. There is a very teasing. There are many have to say that proves that the system behave like integral. However, direct method, they don't work, do not work. That's what I have to say.
Thank you, Peter.